that. And here we go. So, guys, I think you understand where we're headed with this. We are about to jump into chapter 20, oxidation reduction reactions. From having read the chapter, you probably noticed that the chapter is front-loaded with concepts and back-loaded with math. That's how this unit's going to go. Guys, today and next time we're going to talk about concepts. Today we're not going to do any math. The tail end of next time, it'll start to turn mathematical as we begin to calculate the voltages of batteries. And then really the remainder of the unit will be driven primarily by the math that explains the other things that we need to talk about. So, guys, you remember when we did redox? And do you understand redox is the contraction for oxidation reduction? We'll just call it redox. So guys, do you remember redox when we did it in September? Let's talk about what do you remember? It explains why rust happens, although interestingly, we're not going to talk a lot about that. Okay, so we understand that it's the gaining and losing of electrons. Gavin is bravely saying that reduction is gaining electrons, which is actually true. So what then is oxidation? The losing of electrons. And guys, it's important right up front to understand you can't have one without the other. Okay? Now let me explain to you why today's material is going to be a little bit challenging. See, you very quickly, and I'm going to use this as a footstool. Guys, very quickly, you have got to get to the point. This is one of your goals for today. You have got to get to the point where, unlike Gavin, who reluctantly said, reduction is gaining electrons, guys, this has got to be something that becomes fluent for you. Okay? In the same way that when LDS missionaries go into the mission field, they would say that you actually have learned the language of the place where you are when you start dreaming in that other language. Have you heard? You're aware of that, right? Ask return missionaries. Even, your siblings will tell you, you have finally mastered Spanish when you start dreaming in Spanish. And that happens to all missionaries. So, guys, something similar has got to happen to you in here, where you're no longer translating, where you're no longer thinking what you want to say in English and then converting it to Spanish. You're just doing it in Spanish. Well, guys, the same thing's got to happen here to you relative to oxidation and reduction. Very quickly, it can no longer be, okay, electrons are coming in, the charge is being reduced, that means it's called reduction. You just got to be able to look at it and go, oh, that process is reduction. That process is oxidation. The reason you've got to know it that well is because on Tuesday, we're going to start talking about electrochemical cells, and everything that's going on in an electrochemical cell depends on oxidation and reduction, and it's helpful to know it cold. Yeah?
What a helpful way to show the language in a sense is to see which side the 2 or 4 E minus is on the Bell's equation.
The 2 or 4 E...
Where the electrons are.
Absolutely. So, guys, what you're going to find out is that in oxidation processes, electrons are a product. And in reduction processes, electrons are a reactant. And that's the thing, guys, that you're going to see oxidation and reduction in so many unique ways that you're going to have to get your arms around all of those. So, guys, with that said, let's lay down some background. So, guys, at its most fundamental, you all understand that oxidation and reduction involves a transfer of electrons. Now, guys, again, and we talked about this last time, how do we know electrons are transferred if we can't see electrons? What is the outward sign? Ooh, no pun intended. What is the outward sign that electrons have been exchanged? The charges change, the signs change. So guys, what you're going to see is that as oxidation and reduction takes place, the charges change. Okay, so at this point then, we're now ready to start talking about the words that we need to associate with this. So guys, first of all, this thought. When electrons are changed, the thing that loses electrons is being oxidized, and the thing that is gaining electrons is being reduced. So Gavin, it looks like you're going as well. Is that to go to the talk?
No,
It does. I don't need. I was just curious. So guys, relative to the speaker, right? My point in sharing the timing with you was you can be a little flexible in terms of the timing. I'm actually going to go see the speaker as well. It starts at the beginning of lunch. They gave you additional time so that you could get food, but most of you, from having worked with you for months, you've probably already eaten, because you eat right now. And so, and some of you I know don't eat at all. And so realize that you've got some wiggle room because the timing on this, it does start at lunch. So guys, with this idea that the thing that's oxidized is losing and the thing that's being reduced is gaining electrons, let's break it out then. So guys, oxidation then refers to the loss of electrons. Why do we call that oxidation? Because when they first started studying these processes, they found that a lot of things that are oxidized are losing electrons to oxygen. That comes back, Caleb, to your idea of rust. Guys, when a metal rusts, and we will talk about this a little, when a metal rusts, what it's actually doing is reacting with oxygen to form its oxide. And that process involves that metal losing electrons to oxygen. So when they first started studying these processes, they found that oxygen, because it's very electronegative and very plentiful, was really one of the prime movers in terms of causing things to lose electrons, so they called it oxidation. So the opposite of that then is reduction. So guys, well, I'll let you write it down and then we'll talk about it. So we understand they called oxidation because oxygen tended to do that to things, specifically metals. Guys, why did they call the gaining of electrons reduction? Charge goes down, right? The charge is reduced. And so consequently, they called the gaining of electrons reduction because the charge went down. So guys, little rule of thumb here that I like to hang on to. Again, this is early in your language learning process, but when my head gets all mucked up and I need a central truth to come back to, I just like to remember that the charge of the thing that is reduced is reduced. All right, Hunter, how did they teach you to remember this? Or at least they have in years past, depending on who the professor was. Did they teach you the oil rig?
yes.
Oil rig. Oil rig. Oxidation is loss. Reduction is gain. Oil rig. Huh? I know. It does work, though. Did they teach you that one?
Yeah, I think it was.
Yeah, you just repressed the memory.
I did oxidation reduction. They were fun.
Pretty straightforward, though. Okay, so guys, with this as a background, let me introduce you to how this is going to get a little, can I use the word convoluted with you? A little wacky. So guys, you understand this, of course, that you can't gain electrons without something losing them, and you can't lose electrons without them going somewhere. You're going to find out the accounting of this is what makes balancing these equations interesting. But guys, the trick is this. We've got to have oxidation and reduction happening together. So we can look at this through two different sets of lenses. We can say that oxidation is, and rather than writing this down, think through this with me and then I'll give you time. Guys, we can say that oxidation is the loss of electrons, right? And do you notice how I'm talking about this without thinking about it? It's because I understand it. And you need to get there too. So guys, oxidation is the losing of electrons. But guys, watch my hands. So here we've got a thing, and if it's being oxidized, what's it going to do with electrons? Give them away. So where are they going to go? Well, they got to go somewhere, right? And that somewhere that they go, what's going to happen to that thing? It's going to be reduced. But guys, we can also think about it this way. What did this thing do to this thing? So if this thing is oxidized and the electrons go over here, this is reduced. But what did this do to this? It oxidized it. So we can also talk about agency. And when we talk about agency, we're talking about what one thing does to another thing. So come back to my hands, and the idea is this. If this thing is oxidized, it loses electrons. Now turn your attention over here. What did this thing do to this thing? Oxidized it, so this would be the oxidizing agent, and it is in fact reduced. Now guys, we're going to talk about this more in a couple days, but I wanted to introduce you to this idea of agency. So the idea here is that if a substance is oxidized, the electrons had to go somewhere. That thing which is reduced is then termed the oxidizing agent. And then similarly, if something is reduced, it gained electrons, and the place where those electrons came from, which gave away electrons, it was oxidized, we call the reducing agent. And again, guys, we're going to talk about this more on Thursday. No, it's not the acid and the conjugate base, it's the acid and the base. So let's talk about, that's an interesting parallel, but it doesn't quite work. So think about acid HCl, base NaOH, okay? So what does an acid do? It gives away protons, right? Where do those protons go? To the base. So we could then consider the base to be the acidizing agent, because the base is taking the proton from the acid. And so we could think of it as if the base is stealing the electron from the acid, causing it to function as an acid. So it's not about the conjugates, it's about the base being the acceptor, allowing the acid to function as an acid, therefore calling it the agent. Yeah, that's an interesting parallel. I'd never thought through that before. Frankly, my first response was going to be to agree with you, and I'm glad I didn't, because it wouldn't work and that could have caused damage. Okay, so are we okay with these ideas of, well, doesn't matter, because you're just getting started with this. So guys, let me make a suggestion to you as you're doing your homework today. Write as much as you can. I know that some of you like to paraphrase and some of you like to just jot down ideas. Guys, I would highly encourage you on this homework assignment to write incomplete sentences. If you're really feeling brave, you could read them out loud. You could speak your responses before you write them down. Because guys, there's also good research to show that speaking cements concepts. And it's going to be important that quickly you gather these ideas of oxidation and reduction together and be able to speak them fluently, if you will. Okay, so you guys all caught up with me? Okay, so guys, please do not write any of this down on the next slide. I just want to tee up the ball. So there are a couple things in general that you need to know about redox reactions. Please don't write this down. So first of all, redox reactions tend to be spontaneous. They happen on their own. And when this is true, they tend to be exothermic. Certainly they also increase disorder, but that's not the major driving force relative to Gibbs free energy. They tend to be exothermic. That's why batteries overheat. They get hot when they do their thing. And so guys, back to this concept of batteries, what you're going to find out is, especially in this class, we're going to think of these oxidation reduction reactions through the lens of batteries. And batteries are what we call voltaic cells, and we'll talk more about that on Tuesday. Then guys, if you have a redox reaction that is not spontaneous, many times you can force the reaction to go by simply applying a current. This is actually how they electroplate jewelry. If you've got cheap copper and you want to turn it into a silver. It's how they silver plate copper, things like that. But in addition, this is also how a battery charger works. If a battery goes in one direction and creates current, if you want to drive it in the other direction, the non-spontaneous direction, you apply a current to it, and then that recharges the battery, driving the battery in its non-spontaneous direction. We'll talk more about that next Tuesday as well. Then, guys, quickly, we'll also bring in the, you brought this up, Caleb, the corrosion of metals, electroplating. We'll talk about all these things as we go. Okay? Okay. All right. So, guys, with all of that said, let's sort of get down to the nuts and bolts. You want to start writing stuff down again. So, guys, consider this reaction. So it's a classic single displacement reaction. We've got zinc, we've got hydrochloric acid, single displacement producing aqueous zinc chloride, and some hydrogen gas. Guys, the reason, I lifted this out of September's notes. I was trying to bring us back to a place where we could sort of gather and make sure that we're clear on how this stuff fits together. Let's do this together. So, guys, in addition to being a single displacement reaction, this is also an oxidation reduction reaction. So we've got to identify how this works. So, guys, in order to study oxidation reduction reactions, what do we need to know? The charges. We need to know the oxidation numbers. So, guys, this is the way to handle this and the way that we will begin to study redox reactions. We need to know their charges. So, guys, hydrogen's got to be positive, chlorine's got to be negative. Hold on. That was actually not the computer's fault. That was operator error. Okay, so guys, hydrogen has got to be -1 because it's second. So if chlorine is -1, what does the hydrogen have to be? +1. And then, guys, what is the charge of zinc? Well, we're thinking it's +2, right? But zinc is +2 when it bonds ionically to other substances. Do you remember this idea? What is the oxidation number of an element in its elemental form? 0. So in this form, zinc is 0. So, guys, with that understanding, go figure out the charges of the products. Did you get it? Okay. So, guys, chlorine is still -1, so what does that make zinc? There's our +2. Now, what is hydrogen in its elemental form? 0. And guys, understand the diatomics are understood to be in their elemental form when they're in their diatomic molecular form. So hydrogen in this case is 0. So guys, do you see the electrons moving around? What would it look like if we thought a reaction was a redox reaction and we did this and it wasn't a redox reaction? What would it look like? What would it look like if this were not a redox reaction? The charges wouldn't change. Guys, that's often the case in double displacement reactions where they're simply trading partners. But in this example, we do have changes of charge. So whose charge is not changing? Chlorine. So guys, with that said, this is a helpful strategy to figure out who's doing what. Link these guys together with lines. Now, guys, on these lines, it gives you a space where you can actually think through and write down who's doing what. So, guys, let's look at zinc first. Zinc starts at a charge of 0, and it becomes +2. So what happened to zinc? Ooh, it lost electrons. Hey, you guys went straight to it. It lost electrons, boom, oxidized. So guys, zinc is oxidized. Now, how many electrons did it lose? 2. So we can just write down 2 electrons. Now, guys, what happened to the hydrogen? Well, it went from +1 to 0. So what happened to it? It's being reduced, of course. Oh, you were doing so well. So that's being reduced. So now, guys, let's talk about electrons. +1 to 0 is the gaining of how many electrons? 1, but there's 2 of them. So, guys, what you're going to find out very soon is that this accounting has always got to work out. There's not only a law of conservation of mass, there's sort of this unspoken law, which is the conservation of electrons. That's what makes balancing these things so stinking ridiculous. Because, guys, you've got to keep track of electrons as well. Electrons in and electrons out, or vice versa, have got to be equal. So now let's have the last big thought answering these questions. Guys, what substance is oxidized in this process? Zinc. What substance is reduced in this process? Not hydrogen, not hydrochloric acid. Do you not remember when I tricked you with this in September? Guys, what substance is reduced? Hydrogen ion. See? Do you remember when I did that to you before as well? Guys, it sounds nitpicky, but it's critically important. This is obviously not hydrogen ion, but less obviously, this is not hydrogen. Hydrogen ion and hydrogen are not the same. What is hydrogen ion? A proton. So, guys, to call that hydrogen is not the case. It is hydrogen ion. It's really glaring when you think that hydrogen ion is just a proton. But, guys, any element, that's the case. The behavior of the ion and the behavior of the neutral atom are not the same. So it's important that you call that hydrogen ion. They will not give you credit if you were to say hydrogen is reduced. That's not nitpicky. That's a glaring mistake. You okay? Okay. So, guys, anything you want to talk about here relative to writing and balancing these things? You're good? Yeah. 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 So, in what? Well, so the electrons that form that cathode ray are coming from an electricity source, a battery. And inside that battery, there's an oxidation that's losing electrons. So, and the electrons have got to go somewhere, because if the electrons don't have a place to return to, there's no current. So I'm not sure where the parallel. Let's talk about it more later. Okay, so guys, are we okay? All right, so now let's make this more difficult. We've answered all of these questions, so now we're ready to go. So guys, as I mentioned, this gets a little bit wacky. And this gets a little bit wacky because of the accounting for electrons. Guys, this actually gets so wacky that I'm going to give you steps. Do you remember the good old days in chemistry where everything came with steps? How to solve mass problems, how to solve empirical formula problems, how to solve a limiting reactant problem. There was always steps. And then in this class, all the steps went away because nothing's the same twice. You notice that. Well, guys, this is crazy enough. I'm going to give you steps. Don't write this down. This is the introduction. So guys, we understand to this point in our understanding of chemistry that when we balance equations, what we're doing is we're supporting the law of conservation of mass that says what goes in has got to come out. Well, guys, interestingly, when we balance redox reactions, we not only have to balance the particles, but also the electrons. And in order to do this, there's steps. You want to write these down. So guys, it goes like this. Step number 1 is break the reaction into half reactions. And this is what I'm about to teach you is what is called balancing by half reactions. You don't know what they are yet. I'll show you in a minute. But guys, we're going to learn to do these by balancing by half reaction. Truthfully, this is the only way I've ever learned to do these. Hunter and Josh were saying that they learned another way at the U, which you said you didn't like. So,
I didn't understand this. I just stuck with that.
see, I don't understand how it could be worse than this. But certainly it is, or you would have gone with it. Okay, so now guys, you ready for this? Once you've got your half reactions, then you need to start balancing things. So what are you going to balance? Well, you're going to balance other elements first. Then you're going to balance oxygens by adding water. Then you're going to balance hydrogens by adding protons. Once you've got to that point, you will then balance the electrons, balance charge, by adding electrons to the side that is more positive. Understand, guys, you will never subtract electrons. You will always add electrons. And now you're saying, wait a minute, I thought oxidation was the loss of electrons. So shouldn't we be subtracting them? And the answer is yes, oxidation is the loss of electrons, but rather than subtract them, we will make them a product. You'll see in a minute. Then, guys, once you get to that point, as if it couldn't get worse, then you are going to multiply each half reaction by a factor that makes the number of electrons the same. Then at that point, you will add the two half reactions together and simplify. And then once you're done with all of that, if you are in a basic environment, you will add hydroxide to both sides. And the number of hydroxides that you will add will consume all the protons, converting them into water. At that point, you will then check your work and make sure everything does in fact balance, and then finally curl up into a little ball and cry. Oh yeah. So guys, I know I mentioned this before, but I'm serious about this. I have balanced the same two stinking half reaction problems since I started teaching AP chemistry in 2001. Is this my 16th year? I've only done this perfectly once, last year. I'm not feeling good about this year, I gotta tell you. So, understand, guys, you know that sometimes I make mistakes because I know the mistakes you're going to make, and I make the mistakes to show you the mistakes. I'm going to try to do this right. So here's the rules. Just like in chess, the move doesn't count until you take your hand off the piece. Okay? The writing doesn't count until I pull the pen off the board. So I get to erase. Well, I guess I've got to pull the pen off the board to get my eraser. So, when the pen comes off the board, it means I'm sticking with it. And even at that, I know I'm going to screw something up today. I feel it in my bones. Tell me again, you guys are out at 12:10? We may get through both of these. You guys all caught up? You're okay? Okay, so guys, go back, and I know that we've sort of teed this ball up, right? But we've got to talk about half reactions really quickly first. So guys, go back to this reaction. So what is a half reaction? Well guys, the deal is this. We understand that redox has to happen in pairs. One thing's got to lose electrons, one thing's got to gain electrons. So when we think of oxidation, when we think of redox as two processes happening in unison, we can write those two processes individually through what are called half reactions. So guys, with that in mind, remind yourselves, and I've just got to go back to what we had before. So zinc did this. And what was it that caused that to happen? What happened to zinc? It was oxidized and it lost 2 electrons. So now let's go to hydrogen ion, and the hydrogen ion was reduced and it gained 2 electrons. Now guys, what we can do is we can break those processes into individual representations. So this is the way that you do it. Take the zinc, and you may want to write this down with me. What did zinc do? Gain or lose electrons? Lost electrons. But guys, please do not write that down. We will never represent the loss of electrons like this. Instead of that, to represent the loss of electrons, what we will do is this. Get it? So when we lose electrons, what we simply do is represent electrons as a product. You will never have minus electrons. So in oxidation, the electrons will always be a product. Then, guys, for the reduction, we will go 2 protons. We'll gain those 2 electrons and form H2. So that would be the reduction half reaction. So the bottom line, guys, is oxidation, the electrons will be a product, and reduction, the electrons will be a reactant. Which makes sense given our ideas of released, lost, and gained, reduced. Good? All right. Yeah, good. And so the answer is this, and did I do it wrong? These should always be number then charge. The distinction is this. Number then charge denotes the charge of an ion. Charge and then number denotes the sharing of electrons in a covalent bond. So for example, if you were looking at water, technically it should be +1 and -2 because this is a covalent bond. So hydrogen is sharing 1 electron and oxygen is sharing 2. Contrast that with this. Copper oxide is a salt. And in a salt, these are ions and should therefore be written like this. So this denotes charge, this denotes sharing. That said, even in college, I've never had a professor that's held my hand to that fire. Go ahead.
So is that one up there in the blue?
This is wrong.
Okay.
It should be 2+. Let me change that now. Yeah, yeah, thanks for catching that. That should be like this. It should be 2+. I probably need to change it on the other slide as well. All right, are we good? Oh, I'm scared. Here it is. So guys, I love hearing you flip your paper over. You need at least 8, maybe 10 lines to balance these equations. All right, here we go. So guys, you look at this equation and you immediately realize it's unbalanceable because there isn't even any oxygen on the product side. That's a pretty good indicator it's an oxidation-reduction reaction. Okay, so the first thing that we've got to do is split this into half reactions. Now guys, on this one, it's a little simple because you've only got one product. So both half reaction has got to end up in the same product. So one of your half reactions then will be this going to this. Bless you. And then your other half reaction will be this going to the same thing. I'm excited to say I haven't made any mistakes yet. Okay. So guys, once you have this busted into half reactions, it's then time to start going through the steps. So what do we do first? Well, we balance all of the elements that are not hydrogen and oxygen. So for example, here we have 1 iodide, and here we have 3 iodides. So balancing that would be 3I minus yields I3 minus. Then similarly, we will balance the iodines here, and we will go 3iO3 minuses yields I3 minus. Are we good there? Okay, so now guys, we've got all of the elements balanced other than oxygen and hydrogen. So now we start picking at the oxygens and the hydrogens. Now guys, let me make a suggestion that'll help you here. There's no oxygen in the first reaction, right? I would encourage you to rewrite it. Don't let these get out of sync. Bring this down. Come on. And rewrite it. And now here we've got oxygens. How many oxygens do we have? 9. So what we've got to do then is go 3 iO3s minus, I almost forgot the minus, is I3 minus and 9 waters. Okay, so now we have the oxygens. Did I screw up? Okay, now we've got to balance the hydrogens. There are no hydrogens here, but I still like to rewrite this so these don't get out of step. And now, how many hydrogens do we have? 18. So we are going to add 18 protons plus 3 iO3 minuses yields I3 minus and 9 waters. Okay. So now, guys, at this point, I've got a little bit of an advantage over you because I can switch colors. Are we okay? All right. So now, guys, the next thing we need to balance is electrons. Is that right? Is the next step electrons? Okay. Now, in order to balance electrons, guys, what we've got to do is we've got to make the charges on either side of these half reactions equal. So think through this with me. What is the negative charge on the left-hand side? -3. 3 negative 1s is -3. What is the negative charge on the right-hand side? -1. So what we've got to do is make those equal. And the only way we can make them equal is by adding electrons. So guys, if this is -3 and if this is -1, we've got to bring the right-hand side of the equation down to -3. We do that by adding 2 electrons. So what we end up with then is 3 I minuses yields I3 minus plus 2 electrons. think that's right. Okay. Now, guys, we've got to employ the same strategy on the left. What is the total charge? I'm sorry, not on the right equation, the left side of the right equation. The whole thing. So what is the charge on the left-hand side of the second half reaction? Plus 15. Okay. So this is plus 15. This is minus, this is minus 1. Oh, I lost my 5. That doesn't count. That was a board error. Okay, so now, guys, we've got to make plus 15 and minus 1 the same, which means we've got to add 16 electrons to the left-hand side. So we're going to go 16 electrons plus 18 protons plus 3 IO3 minuses yields I3 minus plus 9 waters. Okay, my pen's still on the board. This doesn't count. I think I'm okay. Did I do good? Unless you see a mistake, and then I don't want to hear it. No, what? Really? Did I make a mistake?
No.
Oh, what did, yeah.
How did you get -1 on the right side?
Because, right here, you mean?
Yeah.
Because I3 has a charge of minus 1.
Okay.
And there's only one of them.
And then the waters don't have a charge.
The water's neutral. Yep. So it's only and that's one of the major mistakes you'll make is you'll accidentally leave a charge off of something and it screws all of the charges up. Yeah.
So you always just add charges.
No, it didn't. Yes, you always add electrons, but
So like you're trying to get the left side of that to equal.
you're trying to make these two equal. And the only way that you can do that is by adding electrons. So functionally what you do is you find the one that's less negative. Here it was positive. Here it was negative, but not as negative. And then figure out how to drive that down to the other number by adding electrons. Is that okay? Okay. All right, so now, guys, what we've got to do is well, actually, hold on, stop. There's a check that we can do right now. This is a good place to take a breath and make sure you're okay. So, guys, notice here we have in this half reaction, we have electrons as a product. Is this oxidation or reduction? It's losing electrons. It's oxidation. So again, guys, you got to get fluent with this. I know it's early, but here electrons are a product, which means they're being released, which means it's oxidation. Here electrons are a reactant, meaning it is reduction. Now, what if you get to this point and you've got electrons both on the reactant side or both on the product side? You screwed up. You can't have the same. You've got to have one oxidation and one reduction. Now what we've got to do is make them equal, the electrons. So here we've got 2, and here we've got 16. So what do we have to do? Multiply the left by 8. So now we've got 24 I minuses yields 8 I3 minuses and 16 electrons. Now, guys, at this point, I give myself permission to not rewrite the other equation because I'm now done with this progressive process of balancing. So now what we've got to do is bring these dudes together. I'm going to switch colors again. And now we're going to bring these together. So we're going to, oh, come on. So we're going to sort of draw ourselves a line here. And now we've got to bring the reactant and product sides together. So guys, we're going to start here with the reactants. And we've got 24. That's not a 4. That doesn't count though. 24. Really? 24 I minuses plus, did you see what I'm doing here? That's my only reactant here, but I've got to gather up these reactants, plus 16 electrons, plus 18 protons, plus 3 IO3 minuses, and then that yields 8 I3 minuses plus 6, did I screw up? 16 electrons plus an I3 minus plus 9 waters. I am in the zone. Okay. So now, guys, at this point, all we've got to do is simplify. So first thing is this. If you can't do that, you screwed up. Now what else comes together? So we've got, and guys, you got to be really careful on charge when you do this, because it's not enough to just have the same elements. They've got to have the same charge. So we've got iodides there, but none on the right. We've got protons on the left, none on the right. We've got IO3s on the left and none on the right. An IO3?
No, not an IO3.
Yeah, not an IO3.
I3.
But we can bring these together. Okay, so we've got, right. You know what, guys? I'd rather not rewrite all of this. So would you allow me to just do this? And make this a 9? Okay, so that then removes this. But then, guys, the answer is yes. Not only can you, you have to. You've got to reduce. And all of this is reducible by 3. So that would then be 8 I minuses plus 6 protons plus 1 IO3 minus yields 3 I3 minuses plus 3 waters. And now, guys, at this point, you can actually go through and make sure that your equation balances as we used to do. So how many iodines do we have on the left? 9. And over here we have 9. How many protons do we have on the left? 6. Over here, 6. How many oxygens on the left? 3. And then 3. So it does balance by atoms, but the trick is getting it to balance by electrons, and this is how it goes. So guys, a little bit of advice to you. When you see this question on the AP test, skip it. Seriously, it's worth 2 points and you're going to screw it up. It's not worth it. If you have time at the end of the test, maybe come back and balance it last. It tends to be the last question in a free response question. I haven't seen one in years, but if they have this on the AP test, skip it. You're going to spend 20 minutes on it and still screw it up. So Don't do it. But it is extremely colorful. Okay. Just hold on just a second. So, guys, let's do this. I understand that some of you are going to go. And what I'd like to do is spend 2 seconds and explain to you the one little curveball that you're going to see in these problems. And it goes like this. You'll notice that this took place in an acidic environment. Simply what that means is you've got an excess of protons. What you'll find out is you can also balance these equations in a basic environment. And here's what you would find. The process is, well, let me do it this way. The process is completely the same until you get, well, no, let's do this. Can you guys remember this? Is that okay? Can you not remember it, but feed it back to me. So feed it back to me. So 8I minus. Thank you. Oh, wait. Okay. Okay. So, guys, this is balanced in an acidic environment. What if it was in a basic environment? And the answer is this. If this is in a basic environment, you wouldn't have any of these. Right? What would happen to them? They would react with the OH in the basic environment, and they would turn into water. So here's what you do. If you're balancing these in a basic environment, the process is exactly the same. But when you get to when you're done, and you're like, hey, there's my answer, you then have to do one additional step to respect the fact that it's in a base. And what you do is this. Add 6 hydroxides to both sides. How did I know to do 6? Because it's the number of protons that were floating around. And when you add those, and you guys all understand this is not now the answer to the question, but if it was in a base, it would be. And then what that does then, guys, is it gives you this. 8I minus plus, what happens to those? They make 6 waters plus an IO3 minus yields I3 minuses, 3 waters, and now 6 OHs. But then, guys, further simplifying this, what we end up with then is these 3 waters reduce this to a 3. And now we have an excess of hydroxide respecting the basic environment. Does that ring with what you learned? Okay. So, guys, that would then be this example, which, if I do this and this, that's how this guy balances. But let me show you this one last thing, and then I'm going to get you out of here. So, guys, notice how this works. So we've got copper 2 plus N2H4 yields copper plus and N2. Now we've got 2 reactants and 2 products. So when you write the half reactions, what you're going to do is link up the common elements. So one of your half reactions then would be Cu2 plus going to Cu, because there's your coppers. And then your other one would be N2H4 going to N2. And then the entire process would be the same. And then you would get to the bottom of it all. And because it's in a basic environment, you would add hydroxides to cancel out the hydrogens, the protons. Now, guys, we're going to stop there, and I'm going to stop there with all of you. Realizing that I don't then get to count today as a victory because, frankly, most of the mistakes I make year after year are on this one. So We'll count this as a season that got cut short, so we don't get to count it on our record. But guys, with that said, this is your homework. For those of you, actually, wait. Let me stop recording.